Hello everyone, my name is Subrata Samanta and I am from IIT Kanpur. So, I am a tutor for the physics subject. So, in the previous class, we will calculate the electric field at the center of a arc of a circle. So, we finally got this result that the electric field, the net electric field at point O. So, let us first draw the diagram again. So, if we draw x axis and the y axis, and if we consider an arc, the symmetry about the x axis and this makes an angle theta naught. Okay, the total angle is 2 theta naught since the symmetry about the x axis. So, now we calculate the electric field at this point O, and so again we consider a small strip. Okay, and due to this strip we calculate the electric field. Okay, and the direction is that d vector and the dq. This makes an angle theta and the radius of an arc r. Okay. So, again this one is theta. So, they have two component, one is the these directions, another is the projecting in the x and the y axis. So, and we finally got the electric field E 1 over 4 pi epsilon naught 2 lambda sin theta naught over r times I cap. Okay. So, here only the non vanishing component is the x component, okay, and that is expected from the symmetry point of view. Okay. So, because the at this point, okay, due to the small q small charge dq, so you see that the x component and the y component, right. So, similarly if we consider another small strip here, okay, with a charge dq prime, let us say. Okay. So, due to this charge, okay, we draw a electric field lines. So, again they have a this component, y component and x component. Okay. So, the y component becomes cancelling each other, right, since that this dq prime and dq are basically the same, right, since the lambda is uniform. Okay. The y component of the electric field due to this strip, okay, is the same as the y component of the electric field due to this. So, they cancel each other because the direction is opposite, okay, and the only x component are non-zero and this one is negative, because the direction is minus I cap. Okay. So, this negative sign indicates that the magnitude of then the Ex magnitude is 1 over 4 pi epsilon naught 2 lambda sin theta naught over r. So, when you calculating the electric field due to this kind of system, so you first check that the limiting case, okay, once again. So, if we take the limit theta naught to pi, right. So, again the limiting case, so case 1. So, if we consider the limit theta naught tends to pi. So, if we consider theta naught is pi, then this become a full circle, okay, instead of an arc, right. So, basically the strip becomes a full circle. Okay. And you calculate the electric field as a center of an circle, right. This is the O. So, it becomes, so now we calculate the electric field E. So, we put sin theta naught, then what is the values of sin theta naught? Sin pi, so this one is 0. So, that means the electric field becomes 0. Okay. So, again you use the symmetry arguments. So, if we put an extra arc on this side, right, consider, right. So, due to this arc you calculate the electric field at point O. So, basically this for due to this arc if we calculate the electric field, so this one is in these directions, right. So, they again cancel with this one, right. So, this one due to this first arc and this is considered second arc, okay. The electric field at O due to this first arc in these directions, right, and the electric field due to the second arc in these directions, and they cancel each other. So, in this way if we consider a circle, okay, and I calculate the electric field O. So, each component x and y are always cancelling each others and the net electric field is 0. So, without any calculations you use the symmetry principle and symmetry arguments, okay. So, you will finally end up with the results, okay, what is expected. So, on the other hand, if we consider a small theta naught limit, okay. So, case 2. So, if we consider a small theta naught limit. So, small theta naught case, the sin theta naught is nearly equals to theta naught, right. So, as you know, then so again if we consider a theta naught to be small, that means, so in this limit case what the system looks like? The system looks like a point charge, right. So, we consider theta naught to be a small, system looks like a point charge, okay. So, then the system okay, and the electric field E, the electric field vector E becomes the approximately 1 over 4 pi epsilon naught 2 lambda sin theta naught is theta naught divided by r times I cap, okay. And we know that for a point charge the electric field is minus 1 over 4 pi epsilon naught q over, so this one is r square, yeah. So, if we put r square and then r, okay. So, this is q by r square I cap, right. So, we multiply numerator and denominator by r, right. So, this is the this one is expected, right. So, here the q is the total charge. So, then the q becomes the q 2 lambda theta naught times r. So, if we calculate the total charge of this arc, okay. So, how to calculate? Now, the q, the total charge, this is again lambda times the dl, the integrate, right. So, now we know that the dl is yeah, so r d theta. So, this is not a dl, this one is dq, right. In the previous class we also somewhere is yeah. So, this one is lambda times dq and yeah. So, yeah, so this is right. So, lambda times dl, right, since dq is lambda times dq is lambda times dl. So, then this becomes so if you put dl, it's so lambda is uniform, so taken out of the integral times r again constant taken out of the integral d theta, right. So, what is the d theta? What is the limit of the theta? Minus theta naught to theta naught, right. So, lambda r times 2 theta naught. So, 2 theta naught lambda r, okay. So, this is exactly what I got in here, right. So, that is again the confirm, okay. So, that we recover a point charge limit. So, in this way you always recover a point charge limit in any systems, okay. So, means that for our isolated systems, okay, for this side we always consider a point charge limit, right, at a large values of r or a small values of theta naught depending on the symmetry. So, we extend this problem into a slightly complicated way to extend this problem. We calculate the electric field on the axis of a ring. So, we calculate the electric field. So, till now we calculate the electric field. So, let us consider a, so this one is, let us say, x axis, this one is a y axis, okay, and this one is a z axis. So, now we are dealing in a 3-dimensional problem, and we consider a ring in the xy plane. and this one is a ring. So a finite width. Okay. So this one is the origin O. So calculate the electric field at origin O is 0. Okay. We just saw that before that the electric field at O due to this charge distributions of a ring becomes 0. So now if we calculate the electric field at some perpendicular distance from the origin, I mean in the z axis, okay, at a point P, okay, how to calculate? So this becomes non-zero, okay. And again we consider a limit. So this distance we consider, let us say z. Again in the z tends to limit, 0 limit, at the end we got a result that we expected, okay, at the origin. So okay, so quickly calculate this thing and confirm that the limiting case is that what we got in the previous just before. Okay. So to do the to do this thing, so we first consider a small strip dq, okay, with a charge dq. So we consider a small strip here. Okay, so the length of the strip is dl, okay, similarly as before, and okay, so consider the charge distribution is uniform over the entire ring. So small length element, the charge of a small length element dq lambda times dl, and if the radius of a circle is r, then the dl is lambda r and then d. So we consider this one is a phi, okay. The angle with the x axis becomes phi, so d phi, okay, and the angle with the point P, okay, is theta, okay. So we calculate the electric field at point P. At point P, okay, so that is denoted in the picture. So first calculate the z components, okay. So again we see that from the symmetry arguments, okay. So at point P, so due to this strip with charge dq, so the electric field directions radially outwards in these directions, right. So this is dE vector. So we consider another strip just opposite to the first one, and due to this, if we the electric field at point P, so this one is the other direction. So again the x component and y component are cancelling, okay. So the remaining non-zero value is the z components, and the projecting is a cos theta, okay. So therefore the electric field at point P in the z directions, okay. So dEz dA cos theta, okay. So this one is clear now, right. So we use the symmetry argument and say that the x component, so if we projecting this dy into the x component, into this y component, okay, and z component, okay, since we are considering in the yz plane, and this d we again projecting, so this one is again makes an angle theta with the z axis, and we projecting again y component and z component in the yz plane. So the y component cancelling each other. Similarly, if we projecting in the xz plane, okay, so then again the x component is cancelling each other, okay. That is the symmetry point, okay, the ring symmetry. So the only left is the z component, and this one becomes this, okay. Now if we calculate the d, so d basically 1 over 4 pi epsilon naught times dq. So dq is lambda times r times d phi. So lambda r d phi over, now what is the distance? So this one is r and this one is z, right. So this distance is basically square root of r square plus z square, right, since this one is 90 degree. Okay. So r square plus z square, okay, and then cos theta. So cos theta basically z over square root of r square plus z square. So this one becomes lambda over 4 pi epsilon naught r z r square plus z square to the power 3 by 2 times d phi. Since the whole result, this one is not depends on phi. So integrating over the entire ring, so basically this d phi integral gives a 2 pi, right. So the total field at point P is z, okay, so the total field, okay. So total field means that due to the entire ring, okay. So just we integrate over the d phi, okay, because this the cofactor of d phi is not depends on phi, okay. So this becomes lambda over 4 pi epsilon naught times r z over r square plus z square 3 by 2 and then d phi. So this d phi integral gives a 2 pi, right, of the entire ring, okay. Phi runs from 0 to 2 pi. So this one becomes lambda times 4 pi epsilon naught 2 pi r z over r square plus z square the whole to the power 3 by 2. So now we calculate the total charge. So we calculate the total charge q, so this lambda times dl and then integrate. So lambda is uniform taken outside and dl, so this dl becomes, so lambda times 2 pi r, right, because dl is r d theta, right, and sorry r d phi, in the previous case we define a d phi, yeah, r d phi. So then this is so d phi integral gives a 2 pi. So now we plugging into this, so that means we write down the Ez in terms of q, total charge, okay. So this becomes that Ez at a distance z from the center is 1 over 4 pi epsilon naught qz by r square plus z square the whole to the power 3 by 2, where the q is the total charge of a ring. So again if we plot this, okay, with the functions of z, it look like, so we plot this Ez and as a functions of z. So again we make a dimensionless variable, okay. So z by r, we divided the radius of a ring, and Ez by E naught, okay. So where E naught 1 over 4 pi epsilon naught q over r square, okay. And if we plot this function, so it's look like okay, it looks like this. So almost symmetric. So almost means that is symmetric about the origin O, okay. And at origin O, okay, that means z equals to 0, the electric field becomes 0, okay. So if we check, just put z tends to 0, okay, or z equals to 0. So we put z equals to 0 exactly at origin. So at origin z equals to 0, So, this Ez becomes 0, okay, because the proportional to z, right, and that is expected. Okay. So, from the previous result. Okay. So, we plot that. So, it must passes through the origin, okay, and symmetric about the origin, okay, and it looks like this. So, at some point is maximum, and then again. So, in the next class we will discuss the maximum point, okay, where this electric field become maximum. So, the maximum is at actually 1. So, that means the z at distance r, okay. So, this one is 1. So, basically that at z equals to r, z equals to r, the Ez become maximum. No, we calculate, this is not r, okay. So, we will calculate that that at which point. So, in the next class we will calculate at which points, okay. So, the electric field becomes maximum, okay, and we will also discuss the other kind of charge distributions like the surface charge density and the volume charge density in the next class, okay. So, thank you.